Good morning, everybody. In order to start our notes for today, you want to go ahead and grab a new Topic 7 or Chapter 7 packet. Make sure you get your name down, get your class number down. My class number is 400 or 500 or 600, depending on the class. But write down your class number, 401, 502, whatever it is. And then take your packets and turn them to page 7, I believe. Sorry, page 6. All right, and right at the top of page 6, we're going to go through the different transformations. There are 3 different transformations that we've covered so far, and there's one new one. That new one is going to be the main focus of this chapter. So let's start off with translations. Think real quick, what is the street name for translations? What's another way of saying it? And if you thought of slide, you would be correct. To translate an object is to slide it from one location to another. Just to show you that real quick, here's my object. Okay, and if I want to slide it, I just move it on over. That's a translation. All right, so a quick reminder of what a translation is. Whenever we want to complete a translation, this is how we write it. We do a capital T, and then we put a vector down with the horizontal and vertical distances. If I put a 3 and a -2 there, that gives us specific instructions. It tells us to translate. 3 implies that we need to go right 3. And then this part is our vertical directions, and -2 tells us to go down 2. All right, so we're going to translate right 3, down 2. Now, if you remember, the first coordinate's always x, the second coordinate's always our y. So it's our horizontal coordinate first, then vertical. Now, with our translation, we would have to apply that to an input. So we translate A. And think, what does that produce? If you thought A prime, you'd be correct. Okay, translating an object A, according to this rule, gives us A prime. What about a reflection? Well, first, again, let's go through its street name. What's the gangster name for reflections? And if you said flip, you'd be correct. That's whenever we flip an object across a line. All right, so what does a reflection look like? Well, I can't really do it visually without a grid. A grid just makes it easier to do. So let's say I've got this dotted line that I want to reflect across, and my object is right here. Let me fix that again. All right, if I reflect that across, it'll end up down here. Okay, that's what a reflection or a flip will do. It goes from one direction to the other. Okay, how do we write it? Well, a reflection, like a translation, is started with a capital letter R, and then down below, we need to write down the line that we reflect across. Now, this line that we reflected across, let's call it line L. Okay, so I'm going to reflect across line L. And I'm going to do that to our figure A to produce A prime. We could call it figure B to produce B prime, but we don't need to be too specific there. All right, and that's our reflection. What's our third one? Well, our third one's a rotation. What's its gangster name? If you said turn, you were right on. Okay, so a turn. It's how you turn an object. Once again, let's just see it on a grid real quick. Draw a figure anywhere on this grid, and then just think about turning it. Let's draw this. Nice little cherry there. And then if I want to turn it, I'm going to select it, duplicate it, and maybe I'll turn it like that. Okay, that's a 90-degree turn. Notice how it turned this direction, And it went from one side to that. That's 90 degrees counterclockwise. Quick reminder, counterclockwise is the natural rotation that most things have. Clockwise is kind of the backwards rotation, which is why whenever we rotate, we have positive is going to be counterclockwise and negative will be clockwise. For rotation, we put an R there, and then we need three things. We need a center, a direction, and a distance. And typically we write it almost like a set of coordinates. The direction and the distance are put together. This would be like 90 degrees. But then our center can be a set of coordinates, or it can be the point P, or it could be any center that we call it, that we want to call it. We apply that to A to get A prime. And that is our rotation. A rotation is a turn in a direction, and if it's positive, that's counterclockwise. Negative is clockwise, with a distance and a center. Okay, so we've got center, direction, and distance. If we take a look at reflections, the one thing I wanted to mention is that this is the line of reflection. Okay, and we reflect across that line of reflection. All right, next is our dilation. Dilation is our new transformation, and dilations actually have two street names. A dilation, if you think about your eyes dilating, that means your pupil gets bigger or smaller. Okay, so a dilation is an increase or a decrease in size. We call those either an enlargement or a reduction. Okay, and I want you to take a moment just to think, gosh, if I know what a translation looks like, what a rotation looks like, what a reflection looks like, what does a dilation look like? And if we come over here and do our dilation, it'll look like this. Here is a figure, and a dilation of that figure might make it look like this. We had a small figure, we made it bigger. All right, that is a dilation, and dilations would be a capital D, but then down in the coordinates, it looks a little bit like a rotation, but a little different. It's going to give us two things. The first one is our scale factor, and the second part is our center of dilation. Okay, we would apply it again to a point A or to a shape A, and that produces A prime. SF is our scale factor. And what it really asks is how much bigger or smaller. Okay. How much bigger do I want this object to be, or how much smaller do I want it to be? Do I want it to be 2 times as big, 1 time as big, etc.? This second part is our center of dilation. Just like a rotation has a center of rotation, a dilation has a center of dilation. All right, and with that, we have our 4 transformations. Again, this chapter is going to be all about dilations. We're going to spend a lot of time doing that, but we're also going to compose dilations with the other transformations. So we need to remember what those other ones are so we can do it along with the dilation. All right, with that said, turn the page, and let's take a look at what happens when we dilate an object. Now, over on the calculator desk, you'll find a box with a whole bunch of rulers. Go ahead and grab a ruler. I don't have very good ones, but you'll be able to use them. And what we're going to do is we're going to dilate this object with a scale factor of 0.5. And that scale factor of 0.5 tells us we're not going to make the object bigger, we're going to make it smaller. So we go from P to B, we're going to draw one line segment. Oh, and by the way, pause the video while you guys go and get your rulers and everything. A ruler would be a much better idea than a straight edge because it'll help us to measure some distances. Then we go from P to C. Notice how I'm going past that point. And finally from P to A. And I go past that point again. Notice each of these points are right here. All right, so I want to dilate this with a scale factor of 0.5. What that means is I want to make it half as big. If I look over here, point P is our center of dilation. So we have a center of dilation there. It goes to B, it goes to C. Now let's go ahead and find out the distance to each of those. This is in inches. So you might want to do yours in inches or centimeters. It's your choice. I prefer inches because it's much better. Inches I find to be a much better unit of measurement. All right, so looking at that first one, it's a little over 2 inches. It's 2 1/8 inches. So I'm going to write that down here, 2 1/8. All right, what about the next one? Well, if I go to this one, that one is 3 3/4 inches. 3 3/4. All right, and let's do the last one. Start there, and that is 1 3/4. 1 3/4 inches. All right, so how do I make this object half as big from the center of dilation? Well, all I'm going to do is I'm going to take each of these lengths that I measured, and I'm going to just cut them in half. Since I want the object to be half as big, I'm going to cut those distances in half. So let me come back here. This one is 2 1/8, so I'm going to go to 1 1/16. In order to see that a little bit better, we're going to put it right here. Hopefully we can see that. Nope. 1 1/16 is right there. So this is going to be my B prime. It's half the distance from my center of dilation. Okay, now let's go to C and cut that in half. 3 3/4. Cutting that in half, that's going to give us 1 1/2, the 3 cut in half. And then 3/4 cut in half is really 3/8. So I've got 1 1/2 plus 3/8. 1 2/8, 3/8 right there. So this is where my C prime will be. And then finally, I've got A prime. 1 3/4. So 1 cut in half is half. 3/4 cut in half is 3/8. So I'm going to go 1/2 inch. And then I'm going to go 3/8 further. 1/2 inch is here. 1/8, 2/8. 3/8. Sorry. 1/2 inch, 1/8, 2/8, 3/8 right there. Boom. And that is A prime. With that taken care of, now I can draw my new figure. Well, it's almost perfect. Let's just get that connected like that. There we go. Our new triangle is A prime, B prime, C prime. And we can now cut an object or make an object half the size. Dilate it to be half the size. Now let's quickly write down the dilation transformation so we understand how this works. It's a D for dilation, and then we look at each of our distances, and we realize that they were cut in half, so we're going to do a 0.5. You could also put 1/2 with a center at P, and we're going to apply this to A, B, C, and it produces A prime, B prime, C prime. Okay, that is our dilation by a scale factor of 0.5. Here, you want to dilate by a scale factor of 2. This means we want it to double in size. And what that really allows us to do is to do the same kind of thing that we did before. Go ahead and draw these distances and extend it out. But we're going to take this distance and we're going to double it. So let me actually take this highlighter. Goes from there to there. And now I'm going to double that length. So it goes right over there. Boom. And my new point's right up there. This would be x prime. Okay, that's what I want you to do. Take your lengths and double them. Use the rulers that you have to go ahead and double those lengths. And once you've done that, draw your new figure. Draw your enlarged figure. Now I'm going to cheat a little bit just so I can be done with this a little faster. But while I'm cheating, you guys can go ahead and do it yourselves. If I cheat and it goes too quick, then take a moment to get caught up by pausing the video. It doesn't look like this is going to work. Oh, that did not work either. Man. Alright, let me try it one more time. Nope, did not work. Alright. I always hope it'll work. Nope. Just keeps on going to that regular old rectangle. What if I go like this? Nope. Keeps going to an old rectangle. But you'll be able to double the length. Go ahead and finish that yourself. It should look something like this. Alright, where that's x prime, y prime, z prime, and w prime. Next to this, go ahead and write out the dilation with a capital D. And go ahead and put in the details. Alright, turn the page. If you need some more practice with this, that's what the next page is for. It'll just allows you to practice doing these dilations yourself. Here is PQR, and you want to make it 1/3 the size with the center at M. Here is JKL, and you want to make it 3 times the size with the center at R. Go ahead and test that out yourself. Complete these, just practice it a little bit using a ruler and tripling distances, dividing distances by 3, things like that. All right. Once you're done with that, we're going to move on to, I would say, the far more useful aspect of dilations, because even though being able to do these dilations and being able to do this is useful and it shows a lot of understanding, what matters far more than being able to do that is being able to understand it. We now have modern computers that can do all of this pretty quickly and simply for us. What we want to do is we want to understand how it works and do it and understand what the process would be that it would go through. All right, so let's go ahead and find that out by drawing these connecting lines from P to B, P to C and C prime, and P to D and D prime, and as well as A and A prime, because they're all on the same thing. Notice how each connecting line goes through the original point and its result. Original results. Original image. Original and image. Okay, so it goes through those original points and the image. Now let's take a look at the distance from P to A. Notice how it goes over 1, 2, and then P to A prime is 1, 2, 3, 4, 5, 6. That goes over 6. Well, just looking at the distance between 2 units gives us a lot of information. It actually tells us exactly what the scale factor is. Our scale factor is equal to the new, that distance is 6, divided by the original distance from the center of dilation. So that's 6 divided by 2, which is 3. So this object is 3 times as big, and we should be able to see that. This goes down 3, so this goes down 9. This goes over 2, so this goes over 2, 4, 6. Okay? A scale factor makes something either bigger or smaller, and this one specifically is 3, so it's going to be 3 times bigger. If your scale factor is a number that's less than 1, it's going to be smaller. If it's a number that's greater than 1, your object is going to be bigger. So we've got a scale factor of 3 here. Now, that scale factor shows up if we go to A or B or C or anywhere. And let's take a quick look at that. If I go to B, I go over 2 and then I go up 3. So B prime means I'm going to go over 6, that's 3 times 2. And then I'm going to go up 9, 3 times 3. Notice how those two distances are preserved. One of the things I talked to you about a long time ago was that with right triangles, we are able to use them a ton. And this is one more example of that. Okay, so take a look at this one, and I want you to see if you can get the scale factor. Remember, our scale factor is equal to the new, a length on the new shape, divided by that same length on the original shape. Okay, so that's how we can get a scale factor. Go ahead and get the scale factor for this one. I'm going to pause, or you should pause the video real quick while you guys try and calculate the scale factor. And there are several different ways to do it. You don't just have to start at P. All right, let's take a look. Now, there are a few different ways to do this. The one that I'm going to do is just look at this length here. My new length is 1. But my original length was from Y to Z, and that is 3. So if I were to use my scale factor, my new is 1 divided by the original, that's 3. What if I come over here? This length is 2, that's my new one, and what's my original? Well, 1, 2, 3, 4, 5, 6. My original is 6. So I've got 1/3 or 2/6. Now, regardless as to which one you do, they can simplify. Notice that 2/6 can simplify down to 1/3. Okay, with scale factor, we are going to be simplifying fractions. So if you find those a little difficult, you'll get some practice, and hopefully they won't just not be difficult, they'll also be real useful to you from now on. All right, turn the page. Okay, take a look at this problem. What's the scale factor for this one? Well, we've got a length of 18 on the new shape and a length of 12. That gives us a scale factor that's 18 for our new divided by 12, which is our old. Now, that is a fraction, and notice that each, the top and the bottom, can be divided by 6. 12 divided by 6 is 2, 18 divided by 6 is 3, so that simplifies down to 3/2. Oh, your scale factor is 3/2. If you want to write it as a decimal, you could write it as 1.5. In other words, our new shape is 1.5 times bigger than our original shape. Awesome. Go ahead and determine the scale factor for this one, but also think about it in this other way. We talked about the street name being an enlargement or a reduction. Which one is this, an enlargement or a reduction? Tomorrow we're going to see how we can do this a lot more efficiently if we use a grid. One of the reasons why a grid is so useful. And I can't wait to go through it with you tomorrow. Have a good day.